Okay, we've talked about the basics of equilibrium, and now we need to introduce this idea, the equilibrium constant, Kc. Let's look at a fairly familiar equilibrium reaction. If we have a look at, let's say, the formation of ammonia, so we've got N2, 3H2, reversible, gives you ammonia gas. Now, if you look at the concentrations, first of all, I should say, if you have something in square brackets in chemistry, it's an abbreviation for the concentration of nitrogen, or whatever you have in the square brackets. That's the convention. It's the concentration in moles per decimeter cubed. Right, now if you look at the concentrations of those gases at equilibrium, you will find that this ratio, so if you do the concentration of ammonia squared divided by the concentration of nitrogen to the power of 1 multiplied by the concentration of hydrogen to the power of 3. And I'm sure you can see where those little indices come from. They come from the big numbers in front, which are properly called the stoichiometric coefficients. I usually call them the big numbers in balancing numbers. Okay, that's what they are. And if you look at that ratio, you will find that as long as temperature is constant, as long as you don't change the temperature, you find that ratio is a constant. Okay, and so K is a constant, and usually that's given a little subscript of a C, Kc, and that's what the equilibrium constant is. So for that reaction, that's what it's. And if you have any equilibrium mixture of those three gases, as long as you don't mess about with the temperature, the number of Kc, that number will always be the same. So just another quick one of how do you write equilibrium constant for, say, you've got phosphorus pentachloride decomposes to phosphorus trichloride and chlorine gas. Well, Kc for that reaction, well, the stoichiometric coefficients, the big numbers in front is 1, isn't it, in that case? So Kc for that would be the concentration of PCl3 times by the concentration of Cl2 divided by the concentration of the reactants, PCl5. Just do one more. Let's have SO2. So let's have a 2SO2 reacts with oxygen to give you 2SO3. Well, Kc for that reaction would be equal to concentration of SO3 squared over the concentration of SO2 squared multiplied by the concentration of O2. Right. So let's put a few numbers into those into one of these and work out a value for Kc. Right. So I think we'll use this this reaction here. So we have carbon monoxide will react with hydrogen to form methanol. Temperature is pretty high, everything's in the gaseous phase there. Okay, so you're given the following, you say that the concentration at equilibrium, I'll write Eqm all the time instead of equilibrium, at equilibrium the concentration of CO2, sorry, not CO2, CO, beg your pardon, concentration of CO is 0.800 mole per decimeter cubed. The concentration of all the hydrogen is 0.950, and the concentration of the methanol is 0.105 mole per decimeter cubed. So let's construct the equation. So the Kc for this particular reaction is going to be, Kc is equal to concentration of methanol to the power of 1, concentration of, CO2, that should be CO, concentration of carbon monoxide multiplied by the concentration of hydrogen, and that's got to be squared. So we put the numbers in there, and we find that Kc, okay, is going to be equal to 0.105 divided by 0.8 multiplied by 0.95 squared. So just put that into my calculator, and we find that is equal to 0.145. Now, we need to think about the units there. Okay, what are the units going to be? So we look at this equation, and the units of Kc has got to be the same as the units of all that, okay, on that side. So what have we got there? Well, we have got the concentration, the units of concentration of the methanol, that's mole per decimeter cubed, divided by the concentration, the units of carbon monoxide, and mole per decimeter cubed as well, and that's mole per decimeter cubed squared for the hydrogen. So we can see we can do a bit of cancelling out there. We get rid of them and them. So the units are going to be 1 over mole dm to the minus 3 all squared. Let's expand that out. You're going to get 1 over mole squared dm. Remember the indice rule, so if you square something, you times it by 2, so that's dm to the minus 6. And then if you remember, just write down here, if you remember from, we don't do maths anymore, but GCSE, you had 1 over x squared, that's equal to x to the minus 2, isn't it? So when you bring this up to the top there, what we're going to do with those numbers, we're going to change the sign. So the units for this equilibrium constant are going to be mole to the minus 2 dm to the plus 6, which seems fairly meaningless. So I'll just write the units in there, but that's what they are. Okay, let's think about the size of this number. Okay, so we've got 0.145 there, and bear in mind what it refers to. So you know, it refers to this expression here. So it's less than 1, so you can see this is less than 1. So that means you've got not very much product, and you've got more reactants than product in this case. And it's a good idea to have a look at Kc. So you've got, if Kc is very big, that means the equilibrium lies to the right. In other words, you've got loads of product. If Kc is very small, then the equilibrium lies to the left. In other words, you've got mostly reactants and not much product at all. And you can think maybe if you've got a Kc of 1,000,000 or something like that, so say Kc is equal to 10 to the 6, well, you can say then really, for all intents and purposes, no point thinking of it as an equilibrium reaction. It goes to completion really, doesn't it? Whereas if Kc was very, very small, 10 to the minus 6, say, then you'd have hardly any reactants and all products. You say essentially the reaction doesn't happen. And if you've got a number in between those two extremes, then you do have a genuine equilibrium reaction where you have quite a lot of reactants and products at any one particular time. Okay, so that's just the very basics about Kc, the expression for it, how to work out the units for it, and what it means, the size of it. What does it actually mean? Okay, so we'll leave it there.